So let's just start at the very beginning. What's the derivative of the natural log of x? Well, you might know it already, but here's the process for finding it if you don't already know it. We're going to write this as y equal to the natural log of x. And then we're going to rewrite it using the inverse function, essentially. We're going to rewrite this as e to the y equal to e to the natural log of x. Thank you. And then we're going to rewrite that as e to the y equal to x. Thank you, thank you, thank you. So let me ask you all a question. Easy question. What's the derivative of e to the x? Right, it's the best one ever. It's its own derivative, okay? What's the derivative of e to the stuff? What do we have to multiply by? The derivative of the stuff. Derivative of x is 1. So right, what we're doing from this step to this step is we're essentially using implicit differentiation with respect to x. We're saying y is a function. It's actually really explicit because we know for sure y actually is a function of x. We wrote it right up here. So when you say, oh, I've got the derivative of e to the stuff, I'm saying, oh yeah, the derivative of e to the stuff is really e to the stuff times the derivative of the stuff. And now we're going to solve for y prime. So divide both sides by e to the y. And then we're going to remind ourselves that e to the y, well, e to the y is really equal to x. So y prime is really equal to 1 over x. So the derivative of the natural log of x is in fact 1 over x. Definitely an important derivative to know. And just like with any derivative rule that we have, once you know the basic version of it, you also know the chain rule version of it. Oh, can you brighten that up a little? I can't quite see it.
Okay.
Thank you so much. Okay. So we know that the derivative of the natural log of x is 1 over x. And more generally, we can say that the derivative of the natural log of some stuff is going to be 1 over the stuff times the derivative of stuff. Or as a book, sorry, you would like to see all of that maybe. As a book might write it, the derivative of the natural log of u, where we're saying that u is a function of x, is going to be 1 over u times du dx. But I would encourage you to think of it the way we've been doing it for the whole class, where we're saying, oh yeah, derivative of natural log of some stuff is 1 over the stuff times the derivative of the stuff. And then we're just going to go kind of all over the place with it. So let's say we had f of x equal to the natural log of x cubed plus 1. We can take the derivative really straightforwardly. It's just applying a rule. Our derivative is going to be 1 over x cubed plus 1 times 3x squared. And most people do tend to simplify this. It's literally just a rewriting it as 3x squared over x cubed plus 1. I personally don't tend to because of the way I think about it. I really am encouraging you to think of it as 1 over the stuff and then times the derivative of the stuff. But then you can just write it as, oh yeah, it's really my derivative over the stuff. So if you really wanted to, you can say, no, actually I don't like that. Or we could find the derivative of y equal to the natural log of sine of x. So let's see. That's going to be 1 over my stuff times the derivative of the stuff, which is cosine of x. This particular one I did on purpose because we definitely want to simplify this. This simplifies to what? What's cosine over sine? Yeah. So the derivative of the natural log of sine of x is cotangent of x. This comes back later when we start talking about antiderivatives. So if something's derivative is equal to something else, the antiderivative of that is equal to that. So later on in 17b, we'll be asking questions like, what's the antiderivative of x squared? It'll be like x cubed over 3, because the derivative of x cubed over 3 is x squared. And we're going to ask the question, what's the antiderivative of cotangent of x? And the answer is going to be essentially the natural log of sine of x. So it's good to kind of see these things now, so that later on when we talk about antiderivative, we can have the whole kind of catalog of answers. And really, I should say, to be able to do antiderivatives well, you have to be able to know what your derivatives are. It's just reversing the process. So that's in your future next quarters, antiderivatives. Thank you. So let's look at a couple. Let's do this one first. Let's say our function is y equal to the natural log of x to the 7th times cosecant of x. And I totally could take the derivative of this using the rules we just talked about. I could, and I'm going to this time. I can say, okay, y prime is 1 over x to the 7th times cosecant of x. And I have to multiply by the derivative of all that stuff, which is going to necessitate the product rule. Because the derivative of x to the 7th times cosecant is the derivative of a product. So that's going to end up being, all right, I'm going to write that on top because you can write that on top. The derivative of x to the 7th is 7x to the 6th times cosecant of x. I would normally write plus next, but I know the derivative of cosecant is going to be negative. Instead of writing plus x to the 7th times negative cosecant x times cotangent of x, I'm going to write minus x to the 7th times the derivative of cosecant is the negative cosecant of x cotangent of x. All divided by x to the 7th times cosecant of x. And that's a perfectly correct answer. It's also more work than I needed to do. Here's an alternative way of dealing with this. We're going to rewrite y equals to the natural log of x to the 7th times cosecant of x using the rules of logarithms. So I'm going to say, well, I can break that up as the natural log of x to the 7th plus the natural log of cosecant of x. And then I can even bring that power of 7 down in front and write this as y equal to 7 times natural log of x plus the natural log of cosecant of x. If you're feeling extra special, you could even think about rewriting cosecant as 1 over sine and then writing that as the natural log of 1 minus the natural log of sine. I'm not going to do that because we don't need to do that. So let's see what happens here. The derivative is going to be 7 times the derivative of the natural log of x, which is 1 over x. And the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. And the derivative of cosecant of x is negative cosecant of x times cotangent of x. We can do a tiny bit of simplifying here. It's equal to 7 over x. And over here, you definitely can cancel a cosecant with a cosecant and get minus cotangent of x. Those sure don't look the same. Are they the same? Yes, they're the same. You could totally simplify this if you wanted to. Normally I wouldn't, but just to see they're the same, let's go ahead and do it. If you break this apart as 7x to the 6th times cosecant of x, you don't need to do this part, over x to the 7th times cosecant of x, minus x to the 7th times cosecant of x times cotangent of x, over x to the 7th times cosecant of x. Oh yeah, look. Here, an x to the 6th and an x to the 6th cancel, a cosecant and a cosecant cancel. So you're left with 7 over x. And here, an x to the 7th and an x to the 7th cancel, and a cosecant cancel. You know, for the minus cotangent of x. What I really want to say is, not only is the second way easier to do in the first place, it also kind of gives you a more simplified answer without having to do the work of simplifying. So when you were given a logarithm of something that's terrible, meaning it's got lots of different factors in it, the intent of the person writing the question is that you simplify it first, differentiate it second. And that's usually a good rule of thumb. If you can simplify something before taking the derivative, it's usually a good idea to do so. Especially if you have to take multiple, like if you take a second derivative or a third derivative, it's often a good idea to simplify your stuff before doing the next derivative. Let's look at a couple more examples. Something truly awful. Let's look at f of x equal to the natural log of x to the fifth times e to the x squared over tangent to the fifth of x times the square root of x cubed plus 1. Whoops, maybe you would like to see, if you can't see the things, let me know. I'm sorry. Keep doing that. Okay. We definitely want to simplify this first. I've given questions like this on tests before, and occasionally one person will do it the long way. They'll do 1 over the stuff times the derivative of all that inside part, which is terrible because you have to use the quotient rule and the product rule twice and the chain rule like 3 times. We don't want to do that. We want to make our lives easier. So we're going to break this up. And here's what I want you to see. Whenever you break up a logarithm like this, that's a quotient, every factor that's in the denominator, tangent to the fifth and the square root of x cubed plus 1, those are the 2 factors that are being multiplied together. Every factor in the denominator is going to end up with a negative in front of its natural log. And every factor in the numerator is going to end up with a positive in front of its natural log. So if you really wanted to, you could probably jump to like the full last step of simplification without showing any intermediate steps. I'm going to show you the intermediate steps, but I want you to be okay with kind of jumping further than that. So here's my first step. I'm going to break it up as natural log of the top minus the natural log of the bottom. And I'm going to write the square root of x cubed plus 1 as x cubed plus 1 to the 1/2. Okay, now the natural log of a product is the sum of the natural logs. So that's going to be the natural log of x to the fifth plus the natural log of e to the x squared. And the same deal here. And that's going to be, in fact, let me do this. That's going to be the natural log of tangent to the fifth of x plus the natural log of x cubed plus 1 to the 1/2. But it's minus all of that. Because that whole thing there is the same as that whole thing there. So it's minus that, it's minus that. And then when we distribute the minus sign, we're going to get, oh yeah, the bottom factors are going to have negatives in front of their natural logs. So I'm going to do 2 things at once. I'm going to bring down all the powers. It's going to be, all right? Okay. 5 times natural log of x plus x squared times natural log of e minus 5 times natural log of tangent of x minus 1/2 times the natural log of x cubed plus 1, because the minus sign distributed. And with one small exception, that's as simple as it gets. Small exception being natural log of e is just 1. I should be very, very clear here. We haven't done any differentiating yet. All we've done is simplify the function. But now we're ready to differentiate. I should also point out this third power here doesn't get to come down in front of the natural log. It has to be the power on the whole argument of the logarithm to be able to come down. So now my derivative is going to be 5 times the derivative of the natural log of x, which is 1 over x, plus the derivative of x squared, which is 2x, minus 5 times the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff, and the derivative of tangent is secant squared. Minus 1/2 times, again, the derivative of the natural log of x is 1 over x, So the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. And I probably wouldn't really do any simplifying here. I might rewrite as 5 over x plus 2x minus 5 secant squared x over tangent x minus 3 halves x squared over x cubed plus 1. But I don't really think that's particularly necessary. The only thing that might simplify nicely further is secant squared over tangent, but it doesn't. So I don't think it does. No, really, maybe it does. No, I'm not sure. We should probably check. Does secant squared over tangent get nicer? Secant squared is 1 over cosine squared x. And dividing by tangent is like multiplying by cotangent, which is cosine over sine. No, I don't think this gets any nicer. 1 over cosine x sine x. I mean, you can make an argument that that's nicer or not. It's not worth our time. So I wouldn't bother doing this. Yeah. Questions so far about what we're doing here? Everyone on Zoom, all right? You guys are welcome to ask questions. So just in case any of what I did was kind of unclear about how it was working, I'm just using the rules of logarithms that say the natural log of a product, or really any base, but we operate natural log because that's the most natural base, is the natural log of A plus the natural log of B, the natural log of a quotient is the natural log of the top minus the natural log of the bottom, and the natural log of something raised to a power is that power times the natural log of that something. Those are the 3 rules we were using to simplify these logarithmic expressions. There's that thing that's terrible that I don't really like. Sometimes, no, I'm not even going to go there. We'll come back to that if we need to. What about this? What about different bases? Like, what about y equal to log base 3 of x? I want to find the derivative. There's a couple ways you can handle this. Both of them are perfectly good. And it's really kind of, people have different ideas about how you want to do this. So here's one way you can do this. One way is you can totally rewrite this. You can totally rewrite log base 3 of x as the natural log of x divided by the natural log of 3. It's the change of base formula. And then, I want to be super clear, dividing by natural log of 3 is just dividing by a constant. Or as I would prefer to say it, I've got a constant 1 over natural log of 3 times a function, the natural log of x. And the derivative is going to be constant multiples get to hang out. So it's going to be 1 over natural log of 3 times what? Yeah, 1 over x. People usually write this as 1 over x times natural log of 3. So generally, if your base is something that's not the natural base, you end up dividing by the natural log of that base. So just as another quick example, if our function was, say, y equal to log base 6 of x, the derivative is definitely going to be 1 over x natural log of 6. And there's kind of a nice correspondence between logarithmic and exponential functions that I want you all to be aware of. So here's what I want you to know. You definitely know the derivative of e to the x is e to the x. You guys remember what the derivative of 2 to the x might be? I know it's a little tricky. It's 2 to the x times something. Yeah. Exactly. You can memorize this. There's also the longer route of rewriting. You can totally rewrite 2 to the x as e to the natural log of 2 to the x, which is e to the x times natural log of 2. And then the derivative of that. Well, the derivative of e to the stuff is e to the stuff times the derivative of the stuff, and the derivative of x times a constant is the constant. Oh, that's where the natural log of 2 is coming from. And then this becomes, well, e to the x natural log of 2 is just that, which is just that. Just totally nice. There's a very similar rule that's true for logarithmic functions, which is that if you take the derivative of the natural log of x, it's equal to 1 over x. And if you take the derivative of a log with some other base, instead of multiplying by the natural log of that base, we divide by the natural log of that base. It always works. There's a longer story, which I think we might have time to talk about. But this is the thing I would remember. And so if my base is ever anything other than e, I know that for an exponential thing like 2 to the x, 3 to the x, 5 to the x, I'm always going to multiply by the natural log of the base. And for a logarithm with a different base, like log base 2 of x, or log base 3 of x, or log base 5 of x, I'm going to end up dividing by the natural log of the base. Always true. And it's true even if you have a more complicated chain rule version of the question. For example, I could say, what's the derivative of 5 to the x cubed plus x? Like, okay, well, I know the derivative of 5 to the x is 5 to the x times the natural log of 5. So I know the derivative of 5 to the stuff is 5 to the stuff times the derivative of the stuff times the natural log of 5. And I think most of your teachers are fairly fine with you just memorizing this rule instead of like rewriting it as e to the natural log of 5 to the thing and then doing all the work there. It's probably fine just to memorize this rule. Should be fine. It's usually fine. In a similar fashion, the derivative of something like log base 4 of x squared plus sine of x. Well, I know the derivative of the natural log of some stuff is 1 over the stuff times the derivative of stuff. So I know the derivative of the log base 4. I'm just going to get an additional natural log of 4 in my denominator. So it's going to be 1 over the stuff times the derivative of the stuff. And then also get a natural log of 4 in the denominator, which you would definitely probably write, you would most likely write as one fraction instead of all these different pieces here. You would probably want to write this as 2x plus cosine x, all divided by x squared plus sine of x times natural log of 4. That's probably the nicest way of writing that. Okay. Let's look at one more example before we talk about, yeah, we can do that. So what if I wanted to find the derivative of y equal to log of x to the 6th over secant of x? What should I do before I do any derivatives? I should simplify. Right, that's going to make my life easier when I do this problem. And in fact, I should simplify even further. I should write this as 6 times log of x minus log of secant of x. What's my base? It is 10. Just a quick warning, I know someone's class, it might be a 21A class, it might be a 17A class. Someone is teaching it the log log is the natural log. Sometimes people do that. I'm sorry if your teacher is doing that. It's not terrible, it's just not what most people usually do. So typically natural log, which is ln of x, is log base e, and log of x is log base 10. But occasionally some people like to say that this is log base e. I don't think that's what's going on in any of your classes, but just wanted to warn you. Someone might say that in the future. So if they do, just be prepared for it. So then y prime is going to be 6 times the derivative of log of x is 1 over x times the natural log of the base. And the derivative of log of stuff is 1 over the stuff times the derivative of the stuff divided by the natural log of 10, or times 1 over the natural log of 10. And yeah, we could totally simplify that. This is going to equal 6 over x natural log of 10 minus tangent x over natural log of 10. Leave it like that. There's no reason to try and put this together as one fraction. Okay. But we'd really like to be able to do some more complicated derivatives. Like I want to know how to do the derivative of x to the x. And although there is a rule for it, it's a, I don't want to say dumb. It's not a dumb rule. It's a very complicated rule to memorize. It's not worth your time to memorize the rule for the derivative of a function raised to a function. I do think it's totally worth your time to memorize the rules for e to the x, or a different base to the x, or sorry, no, that's it. Yeah, just really those. But when you have a function to a function, you cannot use your exponential derivative rules or your power rules. Neither of them apply. Yeah, neither of them apply. So let's back up. I'm going to redo the derivative of 3 to the x. Did I do 3 to the x before? No, I did 3 to the x. It's all right. I'm going to do the derivative of 3 to the x in a different way. So we're going to write this as y equal to 3 to the x. And we're going to take the natural log of both sides. By the way, this process that we're doing, where you take the natural log of both sides, is called logarithmic differentiation. And we typically use it if you've got a variable in the exponent. Because taking the natural log, or any log of both sides, allows us to get the variable out of the exponent. I'm going to use the power rule and say, oh yeah, that x can come down in front. And I'm going to rewrite this as the natural log of y equal to x times the natural log of 3. And then we're going to differentiate both sides. What's the derivative of the natural log of some stuff? I know you guys know. Exactly. 1 over the stuff times the derivative of the stuff. Right? Y isn't just like the variable. Y is a function of x. Y is literally 3 to the x. So when I take the derivative of the natural log of y, I'm getting the 1 over the stuff times the derivative of that stuff, which is actually what I'm trying to find. I'm trying to find the derivative of 3 to the x. And that's going to equal the derivative of x times natural log of 3. Be careful here. It's really, really easy to think that natural log of 3 is like a function. It's not. Natural log of 3 is just a number. It's like 1.1. It's a constant. So the derivative of this constant times x is just the constant times 1. If I can say more about this, if people want me to, like I'm really just like, you know, it's just like how the derivative of 7x is equal to 7. The derivative of pi times x is equal to pi. the derivative of any constant times x is equal to just that constant. It doesn't matter that it's written weirdly, it's still just a constant. Do I know what natural log of 3 actually is? I mean, no one really knows what it actually is because it's one of those decimals that goes on forever and ever, that never repeats. But it's still a constant. Finally, solving for y prime, we get, well, I'm going to multiply both sides by y and get y times the natural log of 3. But then I'm going to replace y with what's actually equal to. Say, oh yeah, my derivative is actually 3 to the x times the natural log of 3, which we already actually knew because we know how to take the derivative of 3 to the x. It's 3 to the x times the natural log of the base. It even works for e to the x. The derivative of e to the x is e to the x times the natural log of the base. What's the natural log of e? Just 1. So the derivative of e to the x is e to the x times the natural log of e, which is just e to the x times 1, which is e to the x. So this process works. You can totally take the derivative of something to a variable power in this logarithmic differentiation way, which requires implicit differentiation. And when we take the derivative of the natural log of y, we're using the implicit differentiation and say, oh yeah, the derivative of the natural log of y is 1 over y times y prime. Okay. And we could do this for more complicated things if we wanted to. And for example, if I was going to take the derivative of 4 to the x squared plus 1, you totally could use this process. I don't think you should, because for a constant base to a power that's variable, you can memorize a formula that's not terrible to memorize. You can say, I know it's going to be 4 to the stuff times the derivative of the stuff times the natural log of the base, which is 4 to the x squared plus 1 times 2x times the natural log of 4. You could also do it the longer way, where you said y is equal to 4 to the x squared plus 1, and then you take the natural log of both sides. I don't really want to do that, but you could do it this way. The point is not to do this kind of problem this way, though. The point is that there are actually some problems where we do have to use this method because nothing else really works. And here is what I'm talking about. I want to take the derivative of, say, let's start with the easy one. Let's start with y equal to x to the x. I want to find the derivative of x to the x. And I want to let you all know it's not going to be x to the x. It's also not going to be something where I can use the power rule, which would actually be the same result, because if you use the power rule and brought the x down and made it 1 less, it would be x times x to the x minus 1, but that's just x to the x. That's not the right answer. Definitely not x to the x. So we're going to use the same process. We're going to take the not, and really you should think, whenever I see a variable in the base and the exponent, specifically the exponent, but really the base and the exponent, this is when you should take the natural log of both sides, because you want to get that variable out of the exponent. And the natural logarithm, or really any logarithm, is the only tool we have that really lets us do that. I'm going to take the natural log of both sides. Oh yeah, I'm going to make the next one a little bit less clear. And then we're going to bring that power down. That's why we took the natural log. So the natural log of y equals x times the natural log of x. And now we're going to differentiate both sides. Be careful. In the previous problem we did, when we differentiated both sides, the derivative of x times natural log of 3 was just 1 times natural log of 3, because it was an x times a constant. We no longer have that here. Now we have x times natural log of x. Both of those are functions of x. We're going to have to use which rule? If we have two things multiplied together. Yeah, the product rule. So we're going to take the derivative of the first thing, which is 1, times the other thing left alone, plus, and then I always say vice versa, plus vice versa, right? We do it the other way. We leave the first thing alone, and we multiply by the derivative of the second thing. We want, right, if we call this one f and this one g, we've got f prime times g plus f times g prime. Okay, all that's left is to do a little bit of some, well, not just a little bit. We do have to do more work here because we haven't isolated y prime yet. So what am I going to do to both sides to get y prime by itself? Yeah, I need to get rid of this 1 over y. I'm going to multiply both sides by y. So I'm going to get y prime equal to y times all the stuff that's on the right-hand side, which is the natural log of x plus 1. Right? We can totally simplify that. I think you can probably skip this intermediate step and go straight to saying, oh, well, I know that y is actually equal to x to the x. So when I multiply both sides by y, I can also change the y into the thing it's actually equal to. So my actual final answer is x to the x times the natural log of x plus 1. The idea here is that if you start with y as a function of x, you should be able to write your derivative as a wholly a function of x and know y's should be in there. Let's do a couple more. Yeah, so you can stop me if you have questions, comments, concerns, like how did I do a thing? Did you go back? No, I was going to try and make this one a little trickier. So let's say we want to take the derivative of sine of x to the x squared power. And we notice right off the bat that we have this thing where you have a variable both in your base and a variable. It's not really a base, but like there's not really other good word for it. You have a variable in the thing that's being raised to a power, let's just say base, and a variable in your exponent. We know we need to do this natural log thing, but we're missing something. We need the y equal to part. You can't just take the natural log of the expression, you have to take the natural log of both sides of the expression. If you don't have the y equal to, you're never going to have the y prime when you take the derivative of the other side. So we need to say, oh, we need y equal to the function we're trying to use this logarithmic differentiation process for. And then we can take the natural log of both sides. But we really can't just take the natural log of one side, right? That changes it. If you take the natural log of both sides, you're doing the same thing to both sides of the equation, so it's okay. So then we have the natural log of y equal to the natural log of all this stuff. The power of x squared gets to come down in front. So we're going to have the natural log of y equal to x squared times the natural log of sine of x. And now we are ready to differentiate both sides of this equation. You're almost always going to have natural log of y on the left, and its derivative is always going to be 1 over the stuff times the derivative of stuff. So we're always going to get, well, maybe not quite always, but most of the time when you do this, you're going to get 1 over y times y prime on the left. On the right, it's time for the product rule. The derivative of x squared is 2x. Leave the other piece alone. And then we add, and then we vice versa. Leave the x squared alone, multiply by the derivative of the natural log of sine of x, which is 1 over the stuff times the derivative of the stuff. Okay, I think it's reasonable to jump straight to the final result here. So I'm going to multiply both sides by y, but I know y is really that. So I'm going to say, okay, y prime is going to equal my y, which is sine of x to the x squared, times all of this. 2x times natural log of sine of x plus x squared times, instead of 1 over sine times cosine, I should say cotangent. Because cosine x over sine x is cotangent of x. I think it's perfectly okay to do both those things at once, to both multiply by y and change it into what it's equal to, and also simplify whatever's in here a little bit if you can. But if that's too much at once, take 2 steps, right? It's not terrible to write 2 steps here. I'm just trying to save a little time. Okay. An interesting question. All right, so here's one that just looks neat. I want to find dy dx for x to the y equal to y to the x. So let me ask you all a question. Could I solve for y explicitly as a function of x? Could I get y by itself on one side and just x is on the other side? Easily, anyway. I have no idea. I don't think so. This looks like, I think this looks impossible to solve for y. Like it looks really, really hard to like get y by itself. The point I'm trying to make is that when you have an equation like this where you cannot solve for y, you're going to be using implicit differentiation. And moreover, your answer will probably have some y's in it. So if you can't solve for y easily, when you do the derivative implicitly, your answer is going to have y's in it. Whereas with this previous problem, we already had y isolated. And so when we found the derivative ended up being something with just x's in it. That's not going to be the case here. Our derivative is going to have some y's in it because we can't solve for y in the first place. Okay, so let's see. But before I can do any of that, I've got stuff in the exponents. I don't want stuff in the exponents. I need to take the natural log of both sides. So we do the natural log of x to the y equals the natural log of y to the x. And then we're going to bring down the powers. So y times natural log of x equals x times natural log of y. And now we're going to differentiate both sides with the knowledge that y is a function of x, or as I would say, y is some stuff, right? Y is always the stuff when you're thinking implicit. It's always some more complicated thing than just y. So when we differentiate both sides, I'm going to have to use the product rule on both sides because I have a function of x times a function of x, and I have a function of x times a function of x. So what's the derivative of y? It's like my favorite question to ask. Exactly. I gave you the answer already. It's the derivative of y. So the derivative of y, let me write it down here actually, because I think I'm going to have y prime times the natural log of x plus vice versa. Leave the y alone and multiply by the derivative of the natural log of x, which is 1 over x. On the other side, derivative of x is 1 times leave the natural log of y alone, plus vice versa. Leave the x alone, multiply by the derivative of the natural log of some stuff, which is 1 over the stuff times the derivative of the stuff. And now we're back in our usual solving for y prime situation with implicit, where you have to group all the y primes together and solve. Yeah, you could do that. Sometimes people like to multiply everything by a common denominator to make it a little easier. It's probably a little dicey here since x and y are both variables. It might not really be kosher to do that. So I'm going to just collect the y primes on the same side, and not y primes on the other same side. So you know, y prime times natural log of x minus y prime times, I'm going to say that's x over y, equal to this minus y over x. Factor out a y prime. We got natural log of x minus x over y, still equal to the same natural log of y minus y over x. And then finally, dividing this, I'm going to get y prime equal to the natural log of y minus y over x divided by the natural log of x minus x over y. Kind of funky looking. Not surprising that this has kind of a symmetry to it, because our original equation had kind of a symmetry to it. Yeah, you know, I don't want to do that. That's not going to be good. Part of me wants to multiply by something better. We got time. We got time for one more example. So one more example, and this is the thing this is the thing I was alluding to earlier that I didn't really want to do, but sometimes people do talk about it. So let's say I had something like y equal to 2x plus 1 to the 5th times x to the 4th minus 3 to the 6th divided by e to the x cubed. And I want to take the derivative of that. You could take the derivative of this very straightforwardly, right? You could just use the quotient rule and the product rule and some chain rules, and it would be not the worst thing you've ever done in your life. But sometimes people will say, well, there is kind of a easier method. I put easier in quotes because I don't know if I feel like it's really easier. But there's sometimes people will say, use logarithmic differentiation to differentiate something like this. So we're going to use logarithmic differentiation, which is just the same process where we take the log of both sides, I should say the natural log of both sides, and then use our log rules. So I'm going to say, okay, natural log of y equals the natural log of all this stuff. And the whole point of using it in this particular example is not that we have to, but it's going to make it easier to take the derivative of the right-hand side after we simplify it using our rules of logarithms. Okay, let me show you the two steps I would do if I was breaking down the right-hand side with logarithmic rules. I would first write this as the natural log of 2x plus 1 to the 5th plus the natural log of x to the 4th minus 3 to the 6th minus the natural log of e to the x cubed. I know that every factor on top gets a plus sign, every factor on the bottom gets a minus sign. And then the next step would be to bring down the powers. This is going to be 5 times natural log of 2x plus 1 plus 6 times natural log of x to the 4th minus 3. And this is just going to be what over here? What's the natural log of e to the x cubed? Just x cubed. The natural log of e to the stuff is just the stuff. And now we're ready to differentiate both sides. So now we differentiate. The left-hand side, we're going to get 1 over y times y prime. The right-hand side, we're going to get 5 times 1 over 2x plus 1 times the derivative of 2x plus 1 plus 6 times 1 over x to the 4th minus 3 times 4x cubed minus 3x squared. And then our final answer is going to be y prime equal to y times all this stuff. Where y is the 2x plus 1 to the 5th times x to the 4th minus 3 to the 6th divided by e to the x cubed. And all this stuff is just the same. I'm going to simplify it slightly. I've got 10 over 2x plus 1. I've got 24x cubed over x to the 4th minus 3. And I've got a minus 3x squared. Not necessary to find the derivative here, but probably makes it easier. Again, I'm a little divided on whether I think it's actually really easier, but it's probably easier. It's probably not any harder anyway. How about that? All right. 3:01. I should stop talking. It's been fun. That's logarithmic differentiation for you. Take the log of both sides, differentiate, solve for y prime. Replace y with what it's equal to.